That's better. Yeah. All right. Oh, yeah, that's much better. All right. Good afternoon, everyone. Welcome back. I hope you're having a nice day. It's a lot cooler out there, which is good for a change. Okay, so today we are doing geothermal drilling, but I just want to kind of recap what we talked about on Monday, which was how you do geothermal prospecting. And, I mentioned that it's pretty much analogous to doing unconventional resource prospecting, because you're just looking for large areas that have a lot of hot rocks that are close to the surface. And once you identify that, it's really just a matter of plopping down as many wells as you can to try to exploit that resource. And so, this is an illustration of, a kind of a deep hydrothermal doublet system in the Netherlands, where they're extracting heat from this zone right here, which is shown in the seismic data. And just to kind of make the point here, the way this works is it's just a giant heat exchanger. It's a giant heat pump, I guess you could say, in the subsurface, where they inject cold water down one well, and then they just rely on the flow of water through the formation to the other well. Now, you might be wondering how fast that water actually flows. It doesn't flow terribly fast. So really the cold water just goes down here, and you may not even produce the same water that you've injected. You're just continuously pumping up warm water and just injecting cold water down there. And so it's a really big system. You're exploiting a lot of thermal energy down there. Now, that's not to say that you can't deplete the thermal state of the subsurface if you pump too rapidly or you have too many wells. And there is this concept of they call it thermal recovery, which is after a certain amount of time, the region around the well, particularly where you're injecting the cold water, will eventually cool down, because that water needs to flow through the subsurface, and the temperature pulse needs to dissipate. And so if you're not careful about managing your geothermal resource, you can actually experience a loss in the efficiency of the system if you're pumping too fast. So that's just something you have to consider. It's more of a kind of reservoir engineering aspect, and that's something that I think maybe we don't think about as much, but you do have to consider these things as well. It's not a completely exhaustible or inexhaustible resource. You do have to worry about it kind of running out. Okay, so I think that's all I need to say about this. Okay, so we're going to talk about now the different technologies that are used for drilling geothermal wells, and they range from simple to fairly complicated. But as you can imagine, for shallow systems, it's a fairly simple thing to do. Now, if you're doing one of those horizontal, shallow geothermal systems like you might have in your backyard, obviously you can just do that with a backhoe or some type of an excavator. But if you're drilling a probe well, then you actually need some way of doing it. So you can use augers, you can use a tool that's called a down-the-hole hammer, and then there's standard rotary drilling for deeper systems. So auger drilling, it's kind of like what they used when they were, I think this was like last year, when they were drilling the footings for the foundation of the new building next door. They had a bunch of augers out there, and these are good for very shallow systems where you're like 15 to 20 meters. And it looks something like this. And the nice thing about this is that shallow unconsolidated sediments, it's hard to maintain an open hole in those types of settings. And so you have to worry about the hole collapsing on you before you've actually gotten the stuff in there. But you can actually use a hollow stem auger, and that allows you to drill the hole down, and then you can insert the U-tube into that hollow stem, and then pull the auger out, and then it doesn't matter if the hole collapses around the geothermal probe because it's already in. And so typically what you'll do is you'll drill the hole, you'll get the probe in there, and then you'll grout around the tube that's been put in there. So basically pouring cement down it. So pretty simple system. That's really all there is to it. You just need to carry, some way to dispose of the rock that you've drilled, but it's really not too difficult. If you're going a little bit deeper, there's a different tool which is called a down the hole hammer. And this would be good for kind of shallow but hard rocks. So, if you're in a place like, Austin, where we've got relatively thin soil and then hard limestone right below that, you might use a down the hole hammer type system to get through that. This works. It's basically a pneumatic. It's basically a big fancy jackhammer. You use high pressure air to activate this hammer here, and then you've got these carbide inserts here, which actually do the work of the drilling. And so every time those inserts hit the rock, they break up a little bit, and then you've got to have a way of transporting those cut pieces of rock, which are called cuttings, back to the surface. And so you rely on some type of a drilling fluid to carry those cuttings back to the surface as you drill. And so this type of thing can work in wells that are up to a couple of hundred meters deep. You just need to have a pump at the surface that's capable of supplying the pressurized air to that type of depth. Eventually, you get to a depth where that's not possible. So this is another technique that's used, and this is fairly standard for drilling. These couple of hundred meter deep geothermal wells. Now, if you're going even deeper than that, you can switch over to rotary drilling. So this is what a kind of shallow rotary drilling rig looks like. And those of you who are petroleum engineers or know what a typical oil drill rig looks like, this one looks pretty silly, but it's what you can use these for drilling a couple of hundred meters, and it's got the same working parts as a standard oil field drilling rig. You've got the top drive up here, which is responsible for imparting the rotational motion to the drill pipe. You've got flow lines here which supply the drilling fluid. Again, you need this drilling fluid for the hole cleaning to remove the cut pieces of rock and bring them back to the surface. This is the drill pipe itself. You can tell it's a pretty slender drill pipe that they're using here. And then the flow line that comes back to the surface has the drilling fluid plus the rock cuttings, which go into a settling tank where they settle out and you can recirculate the drilling fluid. So pretty simple process. This can be operated with a fairly small crew. And again, it's, a couple of hundred meters depth that you can get with these. It's actually very similar to what you might drill a water well with. So again, you could have one of these in your backyard if you want to put a geothermal system in. Now, there's several different types of drill bits that you can use on these systems, and they fall into two categories. So there's what we call roller cone bits, which look something like this, and then there's what we call fixed cutter bits. So the roller cone bits look like this, and they've got these cones on them that can rotate independently of the rest of the drill string. And so as these things, as you rotate the drill string, these roller cones kind of walk along the bottom of the well, and they either have teeth or they have inserts that look like this, and they impact the rock and break it up into smaller pieces, which then can be carried back to the surface. And so these are typically used in very shallow environments where you've got unconsolidated rocks or kind of moderately hard rocks, and they work pretty efficiently for that. When you start drilling quite a bit deeper, you have to use what are called fixed cutter bits. And the most common one that's used is what we call a PDC bit, a polycrystalline diamond compact bit. And the teeth here on the fixed cutter are have diamonds in them, which is harder than basically anything you're going to find at the subsurface. And the way that these work is that they, as the drill string rotates, they basically scrape the rock as you drill, and so that breaks up, scrapes off pieces that are then carried to the surface in the drilling fluid. So you can use a PDC bit, you can use a diamond impregnated bit, or you can use a natural diamond bit, again, depending on what the characteristics of your formation are. If you're drilling a very deep well where you're going into like crystalline rocks, like in an enhanced geothermal project, you're probably going to be using a PDC bit because those are the best for those types of rocks. And again, for something like this, you'd probably be using a type of a roller cone bit for those. Okay, so basically, how do you decide which type of drilling technology you're going to use? Well, it depends on how hard the rock is and how big the borehole is. So, for hard rocks with typically, narrower hole sizes, you're going to use the down the hole hammer. Whereas for wider hole sizes, the rotary drilling is generally going to be better for that. This is where geothermal gets a little bit different from oil and gas. A lot of the resource potential of your well has to do with the heat flow coming out of it. And the heat flow is really a function of the heat content of the water that's being produced. And so how rapidly you produce that. So the larger your borehole, the more rapidly you can have heat flow coming out of that well. And so you're going to size your system depending on what you want that flux to be. And sometimes your borehole might be something like 2 feet in diameter, so you can extract as much heat from it as possible. So, that's something that you'd have to engineer the system depending on what the specific characteristics of the subsurface heat source and then your surface facilities are. Okay, so that's the end of that unit. Any questions about drilling that we didn't cover? It's pretty straightforward. We're going to get more into the nuts and bolts of it now. All right. So this is part 2 of drilling. So we're going to cover, in this part, we're going to do rotary drilling for deep holes. Now, this is a typical rotary drilling well for drilling, several kilometers depth. And it's basically the same thing that you use to drill an oil and gas well. It's got the same components of that smaller drill rig that we looked at earlier. They're just scaled up. So here's the top drive. So that's used for rotating the drill pipe and moving it up and down. Here's the drill pipe stacked here on these racks. Let's see, this is the mud pit. This is where you keep your drilling fluid when you're not using it. And then over here, this is the system that removes the cuttings from the drilling fluid and recirculates the drilling fluid. So, again, it's, components are the same as in the smaller system, it's just a lot bigger. Now, when you're drilling a deep well, the drilling fluid properties are actually really important because they help lubricate well, they do a lot of stuff, but they clean the hole, they clean the bit, and they transport the cuttings so that you don't have the cuttings build up at the bottom of the hole. They're important so that you don't have chemical reactions that happen with the rock that you're drilling through, which can be a problem depending on the mineralogy of your rock. They do lubrication of the drill string. They cool it down. You can manage the temperature with it. You need to minimize the leakage of fluid into the formation. We call that fluid loss. And then they control the pressure downhole, which is also an important thing to do. And finally, they impart some type of buoyancy where they support the weight of the drill string and help minimize the stress that's on the top drive. So for geothermal wells, typically you're going to be using some type of a salty water that's mixed with either bentonite, which is a type of clay, or types of polymers. And these help control the rheology of the drilling fluid. So the viscosity, the plasticity, and that sort of thing. And the densities that we're using are typically, on the low end, so close to the density of brine. In grams per cc, it's 1.03 to 1.15. In the US, in the oil field, we actually use pounds per gallon to measure the density of the drilling fluid. And that's, anywhere between 8.6 and 9.6. So, again, if you're used to looking at oil and gas drilling, in those situations, often we're using much heavier mud weights, drilling fluid densities, because we're drilling through, highly pressured zones, which might contain hydrocarbons. But for geothermal applications, a lot of the time we're not dealing with those types of pressures. And so we don't need, as much of the pressure control that you would with oil and gas operations. So it's a little bit different. Okay, so we have to think carefully when you're drilling a deep well about the state of stress in the subsurface. So we're going to talk a little bit of geomechanics and wellbore stability here. So in general, in the subsurface, you can represent the state of stress with three orthogonal components. We call these the principal stresses. And they're strictly defined as stresses that act on three orthogonal planes that have no shear stress on them. So regardless of what your state of stress is, you can always find the orientation of those principal stresses, and they will always exist. We denote them with lowercase sigmas, and sigma 1 is going to be the maximum principal stress, sigma 2 is intermediate principal stress, and then sigma 3 is the minimum principal stress. So this relationship is always true. In the subsurface, usually one of your principal stresses is going to act vertically, and the reason for that is gravity always imparts a force in the subsurface. And so that's often, but not always, going to be aligned with one of the principal stresses. And so because one of them is usually vertical, that means the other two have to be in the horizontal plane, because that's going to be orthogonal to the vertical one. So there are some exceptions to that, but generally you can think of one of these always being vertical. So because of that, in the subsurface, we often use a shorthand where we call the stress that's in the vertical direction sigma V for vertical stress. And then the two stresses that are in the horizontal plane, we denote one of them with a capital H, that's the larger of the two, and then the other one is with a lowercase h, which would be the smaller of the two. And most of the time, not always, but most of the time, the vertical stress is going to be the maximum principal stress, but there are important exceptions to that, particularly when you are in kind of tectonically active settings. So you need to think very carefully about your principal stresses when you are drilling, because they determine how easily you can keep your hole open without the hole collapsing or without fracturing the rock. And so you've got to find what is, we call it a safe mud weight. So this is going to be the density of your drilling fluid that allows you to drill safely without the hole collapsing or unintentionally fracturing the formation. So basically, if you think about looking down at a cross-section of the hole that you're drilling, ideally you just want it to be a circle, right? But what happens is that if your mud weight, which is the drilling fluid density again, if that's too low, you'll have material start collapsing into the well, and you'll get enlargement on opposite sides of the hole. We call this we call these borehole breakouts, and if they get too bad, then you will have the well collapse on you, and that's a bad thing. On the other end of the spectrum, if your mud weight is too high, then you will induce hydraulic fractures around the well. And that's a bad thing also, because what happens when those fractures occur is that the drilling fluid then can leak off into the formation. And that makes it really hard to control the pressure downhole. It makes it hard to transport the cuttings to the surface. So you want to try to avoid this also. And so you have to know what is your range of safe mud weights? And you have to use some geomechanical understanding to do that. So we have to think about what are the mechanisms by which this failure occurs, and then how can we try to prevent that? Okay, so let's take our principal stress system, and I'm going to draw an arbitrary plane here, and it's initially going to be in the sigma 1, sigma 2 plane. So there's our plane. And because this plane is aligned with the principal stresses, we know there's going to be no shear stress on it. It's only going to have normal stresses. Now, if I rotate that by some angle, we'll call that angle C, now this plane will have shear stresses on it because it's not aligned with the principal stresses. And so we can represent the normal and the shear stresses on that plane with something called the Mohr circle. And this is a really useful way of representing stresses on arbitrarily oriented planes. So the way this works is you have two axes here. One is the normal stress axis, and then the other one is the shear stress axis. And what you do is you put 2 points on here. One of them is going to be sigma 1, and the other one is going to be sigma 3. And those are going to lie along the x-axis on a shear stress of 0, because by definition, those principal stresses are normal stresses on planes with no shear stress. And then you connect those points up with a circle. And you can calculate the normal and shear stresses at any point along this circle, and those are going to correspond to this plane that's been rotated by an angle C. And the way it works out is that this angle of rotation in the Mohr circle is twice the actual angle. And so you can see, obviously, when that angle is 0, you're going to be on a plane with no shear stress. But if that angle is not 0, then the coordinates of that point are going to be the normal and shear stresses acting on that plane. Okay, now this is okay for describing the stresses on any plane, but we define a failure criterion by putting a line here and finding the stresses at which that line is tangent to the Mohr circle. So this is a failure criterion for shear failure, okay? And what it says is that at failure, the shear stress acting on this plane is going to be given by this equation here. And it's going to be a cohesion stress plus the normal stress on that plane at failure multiplied by the tangent of what we call the angle of internal friction. That's a material property. And it, again, determines what the failure is going to be. So, you know, this failure criterion is always going to be defined for the material in question, because the cohesion and the angle of internal friction are going to be intrinsic material properties of that rock or whatever you're drilling through. The question is, you know, you're only going to have failure when you are at a state of stress where the Mohr circle is tangent to this line at a single point, or I guess the line is tangent to the Mohr circle at a single point. So you need your state of stress to be such that your Mohr circle does not touch this failure envelope if you want to avoid shear failure. Okay, so that's what this failure mechanism represents. Now, when you do have shear failure, what's going to happen is that the rock or the material is going to break along 2 planes that are oriented at this angle C with respect to the maximum principal stress. And that's what's represented by the fact that there's 2 possible points or there's 2 possible normal and shear stresses that are going on here for your possible orientation. And so we call those conjugate fractures, and those are very typical for shear failure. Okay, now this is all very good. Now, how do we avoid having shear failure? Well, we have to know something about what the stress is in the subsurface while we're drilling, the stresses around the borehole. Okay, so there's this concept called effective stress. And this was really put together by Carl von Terzaghi back in the 1920s, where he observed that the failure of, he was looking at soils, but he observed that the failure of soils didn't depend just on the total stress you were exposing the soil to, but it also depends on the pore pressure of the fluid that's inside the soil. And so he devised this scheme here to explain this behavior. So if I've got a granular material like a rock, most sedimentary rocks kind of look like this. We've got the solid grains here, and then we've got the pore fluid in here. So if I exert a total stress, so if I'm squeezing this material, so what's going to happen is that this total stress is going to be transmitted through the grain contacts. So those grain contacts are all going to have this total stress being transmitted through them. But the other thing you have to consider is that the pore fluid has some non-zero pressure, right? We're going to call that U. And the pore fluid is going to be acting on every surface of every grain in here. If we assume that all the grains are in point contact, so you have an infinitesimal contact area, this pore pressure is acting on all the surfaces of the grains. And it's opposing the contact forces on those grains. And so the actual stress that's being transmitted, if you think about drawing an arbitrary line through the middle of this and doing a force balance on that line, what's actually being transmitted is what we call the effective stress. And that is simply the total stress minus the pore pressure. And this is an important point because when we are drilling and we have a drilling fluid in the borehole, we are changing the effective stress based on what the pressure in that drilling fluid is. Okay. And so what happens is, so if we recast the Mohr circle here, not in terms of just total normal stress, but specifically in terms of effective normal stress, if I increase the pore pressure, you can cause shear failure simply by driving this circle to the left. And so if you're initially at some state of stress where you're not at failure, if you increase the pore pressure, you can get to a point where you actually are at shear failure and cause that to happen. Now, this is kind of a side note, and we don't talk about this in this class, but if anybody has heard the term induced seismicity, this is exactly what happens with induced seismicity. So this is a big problem in West Texas. There have been a couple of kind of magnitude 4 to 5 earthquakes over the past couple of years. And what's going on in West Texas is that the oil and gas operations out there also produce a lot of water. And rather than, the easiest way to dispose of that water is just to pump it back downhole. Well, what's going on is that some of the water disposal wells are close to faults in the subsurface, which are presently inactive. But because they're pumping the water down so fast, it's driving the Mohr circle to the left. And eventually you get to the point where you intersect the failure envelope and the fault slips, and that creates an earthquake. And so this is a big problem that the operators out there have to deal with mitigating, because there was a very well publicized earthquake in Oklahoma several years ago that caused some considerable damage. And so you have to be very careful about where you inject that salt water, because this happens, and it can be a problem. But in the context of drilling, we want to avoid having our drilling fluid cause this type of failure around the well, because that's going to be a problem. Now, so that's shear failure. The other failure mode we have to consider is tensile failure. And so the way we represent tensile failure with our Mohr circle is that we extend the failure envelope down here to the left to represent failure at negative normal stresses. And the shape of this curve, so it's obviously not a straight line. There's a couple of different models for doing this. I think the most common one is what's called the Hook-Brown failure criterion, and that basically this is a scaled square root curve. That's really all it is. And so if your Moore circle gets over here and the left-hand side intersects the failure envelope at negative normal stresses, then you're going to create a tensile failure. And this is what happens during hydraulic fracturing, for example. You inject highly pressured fluid downhole, and what it does is it drives the Moore circle so far to the left that you create tensile failure. And that is, you do that on purpose. But with our drilling fluid, we want to keep the drilling fluid density in a range where we are not causing tensile failure. So again, it's important to know what that tensile failure is. Incidentally, the distance between this point where the failure envelope intersects the x-axis and the origin, that distance is called the tensile strength of the material. And so it's a certain strength you have to overcome, mainly due to cohesion between the particles and stuff like that before you form a tensile failure. Okay, so we've got two failure modes. We have shear failure, where you intersect the failure envelope over here at positive normal stress, and then tensile failure, where you intersect it over here at negative normal stress. Okay, another interesting tidbit about this before we move on. I spent too much time thinking about failure because that's just kind of how my life is. But sorry, that was meant to be a joke. But the other thing is that you can clearly see that tensile failure is going to be favored where your Moore circle is smaller. So that means a smaller difference between your maximum and your minimum principal stresses. And that's kind of an important point, actually, when you think about the state of stress in the subsurface, just kind of in general. But, it's generally not going to be the case that, and well, actually, no, this is an interesting point, because if you're designing a hydraulic fracture stimulation and you've got a large difference between sigma 1 and sigma 3, you're going to have a hard time not just inducing shear failure around the wellbore. And that can be kind of a bad thing, because the shear failure is going to behave differently than the tensile failure when you're stimulating that well. And so there are certain kind of states of stress where fracking just does not work as well because of that phenomenon. So just kind of interesting thing to ponder. Okay, so if we think about the stresses around the wellbore, we can figure out when we're going to have failure and when we're not going to have failure. So very simply put, your wellbore is a cylindrical cavity in the rock. And if we imagine that the rock is a infinite elastic medium that we've put a cylindrical cavity in, then we can think about what the stresses are in the immediate vicinity of our borehole. So let's imagine we're drilling in a very typical setting where the maximum principal stress is vertical, and then we've got our two intermediate principal stresses. The pressure inside the wellbore is PW, and that pressure is going to be due to the weight of the drilling fluid. So that's going to be our hydrostatic pressure within the borehole. There's also going to be some pore pressure inside the formation, which we'll call PP, for pore pressure. So what's going to happen is, because we have a discontinuity in the material properties here, and specifically a discontinuity where the drilling fluid cannot sustain a shear stress, there's going to be a change in stress regime right at the borehole wall. And so there's going to be the horizontal stresses at the borehole wall. They're not going to be sigma 2 or sigma 3. They're going to be what we call the radial stress. and then the tangential stress, which acts in the direction of the borehole wall. So the radial stress always points towards the borehole wall, and then the tangential stress rotates around depending on what position you are on the borehole. Sometimes the tangential stress is called the hoop stress. You might hear that referred to. And so those are the stresses we need to consider, because if we're considering failure on the borehole wall, that's where we are. And so we have to consider what those stresses are. So there's a relationship between the radial and tangential stresses and the wellbore pressure, and then the horizontal stress, the background stress field. Okay, so the radial stress is going to be equal to the wellbore pressure. And that's just simply because that's what's imparting stress on the borehole wall. And then the hoop stress is going to be given by this function here. So it depends on the horizontal stresses, the wellbore pressure, and then the position where you are on the borehole wall. And we define that position as a rotation counterclockwise from the minimum principal stress. And so that gives us this expression here. Now, for any arbitrary horizontal stresses, we can define maximum and minimum limits on the hoop stress. And so we do that by finding where the first derivative of the hoop stress with respect to position goes to 0. So I take that first derivative, and it's a sine of 2 theta. And so that means that that's going to equal 0 anywhere that theta is 0 or multiples of pi over 2. Okay, so it's going to be a periodic function. If we look at the sign of the second derivative, we can tell whether those are going to be maxima or minima. And so the second derivative has this cosine of 2 theta. And so that means for multiples of pi, the second derivative will be negative. So that means those are going to be maximum values of hoop stress. And then for the other values, those are going to be minimum. So we're going to have a maximum hoop stress where theta is 0 or pi. So it's going to be in that direction. And then the minimum hoop stress is going to be when theta is such that we're oriented in this direction. Okay, so that's how we get where those are. So to summarize, that's where the maximum and minimum hoop stresses are. And so if we think about what type of failure is going to happen when we can figure out what direction that the failure is going to be and what the value of the stresses are going to be when that failure occurs. Okay, so let's consider a tensile failure first. So if we pretend the rock has no tensile failure, then that is going to happen when the hoop stress goes to 0, and not just the hoop stress, but the effective hoop stress. So we have to consider the pore pressure. So we represent the effective hoop stress by this term here, that's the total stress, and then minus the pore pressure. And failure will happen when that equals a value of 0. So what we can control here is the wellbore pressure. So, and that's going to be related to the mud weight. And so that means that we've got an upper bound on the wellbore pressure, and it's given by this expression here. So that is the maximum wellbore pressure we can have before we will start inducing tensile fractures on the wall of the borehole. So we want to try to avoid that. Now, we know that the hoop stress is going to be a minimum when we're oriented 90 degrees from the minimum principal stress. So that's when theta is plus or minus pi over 2. So if we plug in that value here for cosine of 2 theta, we end up with this criterion here. So this is the maximum wellbore pressure we can have before we start inducing tensile failure. And if we do induce tensile failure, it's going to happen at an orientation that's 90 degrees from the direction of the minimum principal stress. Okay, so that's tensile failure. We don't want that. This gives us an upper bound on the wellbore pressure. And if you know what that wellbore pressure is, you can figure out what the density of the drilling fluid would be to give you that wellbore pressure at the particular depth that you're at. Okay, so that's tensile failure. Now, the other failure mode, of course, is shear failure. And shear failure is going to happen again when our Morse circle intersects our failure envelope. Now, there's a bunch of trigonometry involved here, and I'm not going to go through the steps. I actually pulled these slides from my graduate drilling class, so there's more math in it. But basically, we have to satisfy this equation here at failure. And so this is all in terms of the principal stresses and the angle of internal friction and the cohesion. And I've put primes on everything here to represent that we're considering the effective stresses and not the total stresses. Okay. So now if we make the math a little bit easier here, let's consider a system where the two background horizontal stresses, so sigma big H and sigma little h, they're both equal to each other. Okay, and we'll call that just the minimum principal stress. So that means that at the borehole wall, we'll have the two principal stresses be the effective hoop stress and the effective radial stress. And we know that the radial stress is the wellbore pressure, and the hoop stress is simply going to be given by this expression here that we derived before. Okay, and at shear failure is going to occur when the radial stress is the minimum principal stress. So that's going to define how big our Morse circle is locally on the borehole wall. And so if you plug in these expressions to this equation here and solve for the wellbore pressure, you end up with this one here. And so this gives us the critical wellbore pressure at which we'll start having shear failure on the wellbore wall. And so this would be the minimum permissible wellbore pressure. And below that, we are going to start having shear failure. So the upshot here is that if the wellbore pressure is too low, you'll start having shear failure. And the critical wellbore pressure for shear failure is given by this equation here. So it's a function of the material properties, the horizontal stress, and the pore pressure. On the flip side, if your wellbore pressure is too high, you will start inducing tensile failure, and the maximum permissible wellbore pressure is going to be given by this equation over here, which depends on the pore pressure and the background horizontal stresses. Now note that both of these equations were neglecting the tensile strength of the rock, and the lower limit here also assumes that the horizontal stresses are equal to each other. But these are going to define what we call the mud window, and the mud window is the range of drilling fluid densities you have to stay within to ensure that your borehole will stay open. Okay, and I will leave it at that for today. Any questions about failure? All right. Well, thank you all for coming, and I'll see you all Friday.